Hello, welcome back to the video lecture series for Introduction to the Art of Programming using Scala. We continue talking about multithreading, and in this video I'm going to go a little out of order for what happens in the book because the example code that we're doing really calls for demonstrating something that is a little bit later in a different section, but it fits very well here. And that's atomic values. And then after we've looked at how we can do the same problem we've been doing so far with atomics, we'll look at how we really should do it, and that's just a smarter way of breaking things into parallel. So if we bring back up our code, you'll remember that we have this where we have 10 threads that we're creating, and they're supposed to count up, and you know, the idea here is it's like we are adding together a whole bunch of numbers, and we are, except in this case all the numbers are 1 so that we know the answer. The problem that we ran into was if we just let this happen in 10 threads, we get horrible race conditions. Okay? And these race conditions cause it so that a lot of the counting gets overwritten, and we don't get the answer that we're supposed to. So in this case, as this is set up right now, each thread is counting to 10 million, so I should have 100 million as my answer, and I was not getting 100 million, wasn't getting anything close to it. To fix this, we synchronized this block of code. So this becomes a critical block because it's something that you should not have two threads doing at the same time, and so we synchronized it. And that worked, but it had the downside that it made our program run quite a bit slower than it would have in one thread. Synchronization is not the only option here. It turns out, so Java added a library called the atomic library. And so I'm going to make a new variable called account. And I'm going to make it equal to an atomic integer from java.util.concurrent.atomic. We'll start it off as 0. We'll import that java.util.atomic, and so that gets imported up in here. Now the name here might seem a little bit confusing. This has nothing to do with nuclear power or anything like that. The term atomic, from its Greek roots, means indivisible. Okay? And of course, when the atom was named the atom, the idea was that it was the smallest piece and you couldn't split it up in any way. Of course, after naming it, we realized, oh wait, there are electrons and protons and neutrons, and then later we learned that the protons and neutrons are themselves made up of quarks. But at least the Greek root of atomic meaning indivisible, that's what we really care about here in our program. And so instead of doing this as synchronized in this way, what we could do is that the atomic count has a number of methods in it that are, that do some operation and return a value. And in this case, really all I care about is I just want to add 1. I don't really need to get the 1 back, but there isn't just an add method, there's an add and get. And what an atomic add and get does is it provides the ability, without the use of full synchronization, to have an operation that adds a value into an integer and returns the new value, and it does so in a way that can't be interrupted. So only one thread can be doing this at a time without actually setting locks on monitors and whatnot. And then if down here we can call account.get to print out the value, and apparently I took out some code there. We don't really need that comment from the bottom. And now we can run this. Notice it's still not fast, but at least using add and get, we'll run it again, see if we get about the same answer. it's running about twice as fast as synchronized, not quite as fast, and most importantly, we are getting the correct answer here. On the downside, it's still running almost 10 times slower than it would have if it were run in a single thread. We were getting it completing in, what, 0.6 seconds in a single thread, and now it's taking 3.5, 3.6. Yeah, so Atomic is kind of an easier and a slightly faster way of doing this correctly, but it's not even as fast as doing it in one thread. And of course, we went to multi-threading so that we could make things run faster. And so I'm going to comment this out as well. So I want to keep these around just so that they are visible for anyone who cares. And now I want to show you how we really should do this. So the problem that we have is really the fact that I have 10 threads that are battling over this one count var. And maybe it's okay for us to have this var. And in some ways, though, if you're doing things multi-threaded, if you can just avoid vars and avoid mutable memory, you have no problem. If 100 threads all read from the same memory location, that's fine, as long as none of them write. And it's that writing that causes problems. And the var allows us to write here. And so that's where we kind of run into our issues. What I'd really like to do, what would work much, much better, is if I had a local variable in each thread. Okay? And then I need to somehow take this local variable C and get it out of the thread. So one way that I can do this would be to create an array of counts. And since I have 10 values here, or 10 threads, I'm going to make an array that is filled with 10 values, and they each start off at 0. So instead of having one counter, I have 10 counters. And each thread is going to use its own local value, and when it's done, it is going to counts sub I plus equals C. Now, once again, in reality, I'd want to do this with something other than just ones. This would be far more interesting if it wasn't just adding one, but then I wouldn't know the answer that I wanted. And then here at the bottom, I can say counts.sum. And that will add up those 10 values. And so if we run this, oh, do I have a typo somewhere in there? Index out of bounds exception. Oh, yes, indeed, I do. Because I went from 1 to 10. Actually, the easiest way to do this, and the way that I would prefer to do this, is to use the indices of the array. That way I can feel very confident I'm not going to run out of bounds. Notice I have the right answer, and not only do I have the right answer, I have the right answer, and I got it even faster than what it went in a single thread. And so we can run this again, make sure that wasn't just a fluke. Oh my goodness. Bingo. There we go. So the appropriate way to do this is to make it so that the threads don't all have contention for a single count. And in fact, there are other ways that we could do this that are more Scala-like. We're still playing with the Java libraries. By the end of this chapter, I'll show you kind of how we can take this code even further and add it and do this same operation in a way that's very simple and that has a Scala flavor to it. But at least here you can see that by keeping separate bins for each thread and making each thread work kind of on its own locally, and then here adding the bins and doing this, even if I didn't have the bins, okay, so just let's look at one other way that I could do this. Cut out that, and I am just going to output count. And once again, well, how do I do the counts? This is not safe. I can't just do count plus equals C, because the other threads could interfere with that. Let's go back to, well, actually, I guess I can uncomment that, just not use it. But I could synchronize this. I could say multithreading dot synchronized on that. Now, we were saying earlier synchronization is problematic. You can't do it that much. It can slow things down. Well, that's when we were doing synchronization 100 million times. Now I'm only doing the synchronization 10 times. Every thread does it once, and it's the last operation that happens. And you can see here, wow, if I believe that timing, oh my gosh, this is even faster than using the array. Of course, it's, you can see they're jumping around a bit. But this works very well too. The main thing is that I don't want to store it all. I don't want all of my operations, this individual adding, to be happening in a single value. I want it to be happening so that every thread has its own, and it's only at the end that those things get compiled. So that's it for this video. We'll come back next time and we'll look at some more constructs that we